Okay, guys, so thank you for attending the webinar. I welcome everyone, because of Spartificial. Okay, so yeah, so let's jump in. Okay, everyone able to see my screen, right?
Yes, sir.
Okay, great. Okay, great. Okay, okay, guys, so let's inaugurate our event. So it's a webinar on machine learning for rockets. Okay, so what do you see here? You're actually seeing the lunar surface. Okay, on the lunar surface we are landing the rocket. It's a NASA rocket. Obviously it's an illusion, it's not real. And from the rocket there's a rover just jumps out from the rocket, and you can see the astronauts and you can see the flag. Okay, and in the side you are just seeing the code. The code, it is written in Python, some basic code, right? If speed, if position, else, some basic stuff. So this title slide itself good enough to talk about importance of programming skills, AI, data science skills on our rocket science. Okay, yes. So let's get in. Yeah, like I told already, I am Sudeep. I am head faculty at Spartificial. Previously, I was with the Noor Islam and Pine Global. I was a faculty. I was a data scientist. Okay, here I am a head faculty doing stuff. So let's begin with what is a rocket. So whoever attending here, everyone attending here must be familiar with rockets, right? So you don't need a definition for the rocket. So rocket is a launch vehicle. Okay, which rocket is a launch vehicle which carries the payload from the ground, the Earth, and discharge that payload to the orbit. Okay, so that payload could be a spacecraft. That payload could be any other space vehicle which could able to get into deep space, something like a Voyager. Okay, that spacecraft could carry the rover to the Mars. That spacecraft could carry the astronauts to the lunar. Okay, or that space ship could carry the astronaut to the ISM. So anyhow, we need a rocket to launch any object, something which is known as payload, from the ground to the orbit. Okay, we need rocket launch vehicle. Without the launch vehicle, it is impossible to escape from the Earth. Okay, impossible to escape from the Earth. So how does this rocket work? So it is. There are so many principles. Okay, according, I mean, relating this rocket theory. So we are not actually checking that. Okay, we are not here actually for that. We are here for ML, how machine learning particularly helping the rocket. Okay, we are here for that. So how exactly rocket works out? Rocket is pushing downward, pushing out the exhaust, the hot jet exhaust. Okay, or some latest rockets in future could able to push out the cold jet, who knows, or push out some cryogenic jet, or push out something else. But the ultimate intention here, by pushing out something, we can obtain the momentum. We can use that momentum to propel the rocket. Okay, thereby rocket could move to the certain distance. Okay, and we keep on pushing out the exhaust. Thereby rocket keep on moving up, and there will be perturbations. There will be disturbances here and there due to a lot of atmospheric conditions, something like solar radiation, something like aerodynamic pressure differences, something like wind gusts. There would be too many differences, lot of differences. So these perturbations and the disturbances caused by the perturbation will be tackled up by control system. Okay. So rocket control system taking readings about the perturbation, matching it with pre-programmed trajectory, matching it with pre-programmed trajectory and taking the remedial courses, altering the rocket in the right orientation, thereby achieve the destination. This is how rocket usually works out. Okay. So if we talk about rocket engine design, if we talk about the fairing, the staging, the structural health monitoring, if we talk about controllability, control station contributor, if we talk about any other parameters, okay, that would be, it's possible to talk, but still we are reducing ourselves for the point of interest, which is machine learning. Okay. So this is rocket people. And yeah, in the history of our human achievement and scientific progress, this Apollo missions was the key player. Okay, in 1969 we launched, I mean NASA launched Apollo 11, and that carries astronauts. Okay, and the rocket they have used was Saturn V rocket. Right after this, we are sensing tremendous changes in the revolution of rocket science and development. And here I am showing you the available rockets. The available rockets possessed by different countries, I mean the different agencies in different countries. Here you can find most of the rockets possessed by United States. Of course, India is also having a rocket, which is a PSLV. And this slide is also covering so many rockets. We have a GSLV, okay, and of course uh, we can see, one second, we can see the United States flag once again higher in underneath the rockets, okay, because they are the key player in the space industry. Obviously they possess a lot of rockets, okay. And when it comes to ISRO in India, ISRO is the key player. Obviously they have also launch vehicles, and few launch vehicles are under development. In the development, you can see the reusable launch vehicles, technology demonstrator. So here you need to take a point, what is reusable launch vehicles? And obviously launchers are retired, is nothing but SLV3 and ASLV, and launchers under use PSLV, GSLV, okay, GSLV Mark II, GSLV Mark III. So obviously it's a business, right? It's quite a booming domain, the rocket science, how rocket science is assisting space exploration, how space agencies are doing the space exploration with the help of rocket science. Okay, so obviously it's a booming domain. Now, who is this guy? So I told about reusability of rockets. So that idea was initially proposed by Elon Musk, okay, because he himself found that the cost for a rocket launch and the dismissal of the rocket parts to the ocean, okay, that is somehow harming the space industry, okay, of drawing more cost. Okay, so he decided to produce prototypes which could be reusable, so that space industry could be able to reduce the cost. So his reusable thought lead the research domain known as autonomous landing of rockets. Okay, he is the founder of SpaceX. Am I right? SpaceX. So there, he checked numerous prototypes, and a couple of prototypes got success, which are Falcon 9 and Starship. Of course, Starship is still under development, but still everyone is talking about Starship because one day it will carry humans to the Mars, and it will safely land on the surface. It will safely land on the Mars planet surface. Okay. So we can able to reuse the rocket just like how we are reusing car, just like we are reusing bus, okay, just like how we are using other vehicles, okay. We can able to reuse the rocket, thereby we can reduce the cost of launching the rocket, okay. So this is the idea of Elon Musk, proposed the theory reusability, and he achieved it, okay. And he's um, the person exampled everything, okay. So So far, what we have done, we discussed about the origin of rockets, and we have checked about some launch vehicles, and we have checked about idea of reusability. Now, please have a quick look on AI and machine learning. Okay, then we will get into how we can apply AI or machine learning in rocket science. Okay, first quickly check this AI and machine learning. So what is this? What is this? So artificial intelligence. What is that artificial intelligence? How we can compare artificial intelligence with the human abilities? Okay, artificial intelligence is nothing but a system, intelligence system. It could able to think more accurate. Okay, superstitious thinking, superstitious decision making, a quick processing of taking the decisions. Everything is done there with artificial intelligence. It is a good replacement for a human being. Obviously, it is mimicking ourselves, but thinking way better than us, taking decisions way better than us. Okay, humanoid are not just one and only artificial intelligence systems. Okay, artificial intelligence is nothing but a system, a software. That software could be developed by a tool, by a technique known as machine learning. Okay, artificial intelligence systems could be developed by machine learning. Okay, and this machine learning is powered by deep learning. Machine learning is powered by deep learning. Okay, so deep learning is a subset of machine learning where we are building architectures which mimic our artificial neuron. Okay. And this deep learning technology is powering up machine learning. How, where now, where we can fit the reinforcement learning here? What is obviously reinforcement learning? Why that is really important? How we can differentiate reinforcement learning with other mode of machine learning components, which is supervised learning and unsupervised learning. We should know about that, right? So supervised learning, unsupervised learning, reinforcement learning, both are different part of machine learning. And deep learning could be applicable on these parts. Deep learning could be applicable on these parts, could be able to power up all these parts. Okay. Finally, by doing all this, we can accomplish an artificial intelligence system. That's how things works out. So in the upcoming slide, we will see more about what is supervised learning and supervised learning, how we can differentiate those with reinforcement learning. Okay. Here we go. Before that, let's quickly check the differences with respect to the application. So if you take out reinforcement learning is mainly applicable or mainly getting applied over robot navigation, autonomous behavior, okay, and control system behaviors. Something like a robot, if you take out any robot, the movement of the robot, thinking of the robot, actions of the robot will be powered by reinforcement learning a lot. Okay, you can ask whether is it possible to apply supervised learning and supervised learning there. Of course, it is possible, but the accuracy, the optimality, okay, is quite low when it compared when we are applying other mode of learning rather than reinforcement learning, okay, on robotic science. Okay, and when it comes to supervised learning, it could be divided into two categories. One is regression use case and the classification use case. And we are doing numerous projects, okay, by using regression and the classification. And if you take out unsupervised learning, the main important application recommender systems and main important features are clustering and dimensional detection. So this is how we can differentiate the components of machine learning with respect to the application. Okay. And simply how we can understand these three. So supervised learning. If you take out supervised learning, see there's a blackboard and there's a professor and there's a student and on the blackboard there's the content. Okay, so what is happening there? So professor is teaching the content to the student. Okay, this professor is actually the label or the hint or the supervision about the data. So the data will be given to the AI model. Data will be given to the AI model, coming up with labels, coming up with hint. Some supervision is there. So the model would able to understand its element, would able to easily grasp everything, okay, would able to produce nice predictions out of it. When it comes to unsupervised learning, there's a person just sitting. That person is actually a model. Okay, just flipping over all the pages and reading the content one by one. Okay, flipping all the pages, reading the content one by one. Okay, definitely at one state, definitely the model will get the pattern, the right pattern, where the right information, but no supervision is there. No hint is provided there. Okay, the model has to learn everything from themselves. But again, we have beautiful algorithms to achieve this job. Okay, and when it comes to reinforcement learning, okay, what you see here, a robot. Okay, think about a rover in a Mars surface. Think about a rover in a Mars surface. Okay, even though that particular robot has already been involved with a lot of simulations, groundwork, that environment is completely new, right? Completely new. So as soon as the rover landed on the Mars surface, it has to think itself where to move, how to move, where to do the research, how to collect the samples, what was the data. Okay, everything it has to do by itself. Okay, it has to explore the environment. It has to learn the environment by exploring, and it has to take the optimal decisions in the right way. Okay, so this is how we can differentiate briefly supervised learning, unsupervised learning, and reinforcement learning. Okay, yes. And why Python? Okay, so we use this Python programming language mostly for data science related to AI. Reinforcement learning is part of the AI. Deep learning is a subset of AI. So Python obviously is supporting data science. Why? Because of its community support, because of its platform independence, because of the code simplicity, and because of the availability of large set of libraries. Okay, Python is the one we are using for data science as well as for AI. Now this table, okay, will give you much better comparison about these three kind of learning. One is supervised learning, unsupervised learning, reinforcement learning. Okay, you can check the applications. You can see the self-driving car, gaming, healthcare in reinforcement machine learning, and you can sense recommendation system in unsupervised learning. Okay, so you need to go through this slide later to have much better understanding about these three divisions of machine learning. Okay, so with this, I am just stopping the introduction about artificial intelligence and machine learning. So now we know about rocket. Like I told already, rocket is a launch vehicle which carries the payload, an object from the ground and discharging that to the orbit. Okay. And definitely that rocket is powered by digital control systems. Okay, the rocket is powered by environmental readers. Those are must be digital. So, so rocket parts usually most of the parts, okay, should come with digital nature. Okay, you may think wherever there is a digital, that digital tendency could be improvised by AI. So that's it. The story of AI with the rocket. Okay, don't just conclude there. Okay, so AI is not only just used in the control systems of the rocket. Okay, AI used in all elements of the rocket. It could be, it would be in future. Okay, so how? The very first chapter of our webinar, which is a faster way to design rockets, scientific machine learning. Okay, the faster way to design a rocket. Why designing a rocket should be quicker, should be faster? Why? Why there's an emergency? Okay, because I don't know how many of you coming from aerospace background. So whoever coming from aerospace background and mechanical background knows very well about simulation softwares, design softwares, especially simulation softwares, when to iterate the simulation about getting the solution. They are very much familiar about how much time it would take. Even after spend month or 30 days, 40 days for a complete rocket design of engine, the outcome comes out of it will it be accurate at all time. Okay, so designing a rocket usually done by conventional software packages or tools. At that place we can able to apply machine learning. Okay, we can be able to apply machine learning and we can make a blend of whatever already there already exists in the name of designing and development of rocket. There we can apply the machine learning, we can make a blending, there we can create the super models, a super approach, super technology. Okay, that is how we can use scientific machine learning in rocket designing and development. Rocket designing and development. If you take out any vehicle, if you take out any vehicle, there should be a design. That design should be approved after the performance checking, simulation. Then there will be manufacturing. Then there will be testing. Okay, so if the design and development is not accurate, not good enough, not quick enough, okay, definitely there will be some issues, not supremacy, not outstanding performance of providing. Definitely when it comes to testing, there will be issues. During manufacturing also there will be issues. Okay. So design and development should be made with high level accuracy. Okay. So that is where we can use the machine learning. And trust me, this is the very hard leading research domain, how we can introduce the machine learning into conventional design and development packages. Okay, so first of all, let's understand, let's have a quick look over what are the current design and development and analysis softwares in industries, space agencies using for the rocket development, okay, rocket building. So for the design, okay, space agencies are using CATIA V5 unigraphics for structural, thermal, and vibration analysis. This part comes after the development, I mean during the development, the performance checking. Whatever design you have made, you need to do the performance checking, right? So those performance checking could be done by ANSYS, Siemens, NXPLM software, okay. And we have an aerodynamic property. So aerodynamic property, what is this aerodynamic property? Rocket will be flying through the atmosphere. Okay, the environment is completely atmosphere. It's a fluid. So that fluid will be reacting to the rocket, causing perturbations. There will be torque, there will be momentum disturbance. So some sort of aerodynamic study should be made after you design and develop your rocket in the sophisticated lab. You have to make aerodynamic experimentation. That is currently done by CFD softwares, okay, in industry, in space agencies. When it comes to academic, okay, academic point of view, people are doing many projects, tutorial projects, relying on a lightweight applications known as open rocket or as aero rocket propulsion, a lot, okay. So what is the drawback of these approaches? What is the drawback of these approaches? Why this intelligence, I mean AI, is blending with these approaches? Okay, we really need to know that. Okay, because to design and to develop and to test the rocket, there are so many parameters we have to consider. Okay, temperature, pressure, velocity, attitude correction, okay, and vibration analysis, health monitoring, a lot. Okay, the technology we are right now having to simulate everything inside a laboratory would take so much time. Okay, would take so much time, months and sometimes years. Okay, people are really worrying about the time taken, the duration current approaches would take to define the right design, okay, the best simulation. That is actually happening there. Okay, it just too much time requirement. Okay, so we really need to get away with that. And even with the help of supercomputers, nowadays these computer simulations taking months and weeks. No one would like that. Okay. So to speed up this design process as well as to bring out highly accurate predictions in the simulations. Okay. Because forecasting is really needed. Forecasting is important when it comes to simulation. When we are checking the performance of a rocket, whatever we designed, there must be a forecasting. That forecasting could be powered by AI a lot. So we can blend that here. So for these reasons, definitely these technologies should be blended with AI. Okay. And here we go. Physics-based reduced order models. Who is this scholar? This scholar is nothing but Karen Wilhobbs. He is the director of Warren Institute. He proposed these models, physics-based reduced order models. What is this actually? So these physics-based reduced order models are nothing but a blending of machine learning to the physics-based modeling. So whatever we are doing with the help of CATIA, with the help of ANSYS is known as physics-based modeling that requires some physics simulate physics equations, 1D equation, 2D equation with respect to the various parameters. Okay, so those are physics-based modeling. So those physics-based modeling will be blended with machine learning. Thereby, we can create reduced order models. Reduced order models. Okay, what is the significance of these reduced order models? So just like Karen will have told, the big decisions need more than just big data. They need big models too. What do you mean by big models? High complexity models. Okay. The architecture layers of the model is keep on increasing. Okay. The complexity would be increasing. We need a big model. Thereby, it can adapt a big data. Okay, thereby it can able to cover more problem areas. Okay, that way we can introduce machine learning there efficiently and we can take the predictions efficiently. Okay, so here this reduced order model is trained with the help of a data set provided by GEMS, general equation and mesh solver. Okay, so this is actually coming from combustion simulation code. Okay, so right now we are just looking at the rocket engine. Okay, for the sake of understanding, just clear out your mind and have a thought about rocket engine, just a rocket engine. So our intention right now is to design a rocket engine. So rocket engine internal behavior is powered by combustion, right? So there will be combustion simulation code generated by Air Force, okay, from coming from United States, and they are having this GEMS data. Okay, this GEMS data is the data required to create reduced order models. Okay, so this reduced order models, when created, it would need snapshots of what is happening inside the engine. Okay, after you designed your engine, when it comes to performance testing, you just need to take a snapshot. Okay, this snapshot again, not a camera picture. Okay, this is again a simulation. This is the temperature profile, pressure profile of what is happening there. Okay, the simulation. We just take that simulation as a snapshot, send those to the model we develop. The model will predict exactly what would happen for the entire working span. Okay, this is known as forecasting. So this is how we can use the machine learning in a rocket engine. Okay, rocket engine design and development. So we are not only using the machine learning in rocket dynamic behavior approximation. We are using machine learning very first hand when we are designing the rocket and developing the rocket. Okay. So this idea was proposed by Karen Behaks, and research work is going on there actively. Okay, and how exactly this reduced order model simulation doing better than alternative rocket design softwares? Like I told already, the simulation will be recurring more time. Okay, it will recur very less time. Okay, and these models are big models, high complexity models. Okay, so it cover up more areas: temperature, pressure, vibration, everything it cover up. Okay, so according to the simulation results, we can able to come back and change the design aspect. Thereby we can finalize the right design. Okay, this is not only applicable in rocket engines. If you take out any other parts of the rocket, okay, then also you can use these machine learning kind of reduced order models, but you need to build your own model. Okay, this building of this own model is falling to the category of supervised learning. It's not a reinforcement learning. Okay, but you need to build your model for the use case with the data. Then you have to use the snapshot of the data as a test data. Thereby you can able to predict or forecast the entire performance of the particular part of the rocket. Then based on that feedback, you can able to correct your design and you can finalize your design. Okay, but this could be done in conventional simulation softwares, but the problem, very low accuracy, because too much time is there. Okay, too much time it would take. But when we are introducing machine learning there, it would take very less time. Okay, I think you got the idea. So yeah, here I'm just showing you a couple of papers which is doing research over the topic we discussed. Okay, so formulations for physics-based machine learning. Okay, projection-based model prediction. Exactly the same idea. This paper was released in 2019, and see, learning physics-based reduced order models for single injector combustion process. Combustion process is what happening inside a nozzle. Okay, so there they are going to introduce the reduced order models. The paper got published in 2020, and see machine learning methods for the design and operation of liquid rocket engines. Okay, it's a conference paper published in 2021. So complete design and development. Okay, design and development as well as operation of liquid rocket engines powered by machine learning method. Okay, you just need to go through these slides once again. You will definitely get an idea completely about the rocket design, how each part of the rocket design powered by machine learning techniques. Okay, especially using reduced order models proposed by Kate Wilcox. Okay, great. This is the next chapter. So rocket stability and autonomous control powered by machine learning. Rocket stability and autonomous control powered by machine learning. Okay, so we know very well about autonomous control, I suppose, because we know about satellites, we know about satellite docking, we know about orbital injection. So satellites keep on revolving around the Earth. So no pilot is there to operate the satellite. It is operating by itself, right? That is autonomous stability and control. And just like the rockets, not most of the rockets, I mean, no rocket is powered by, I mean, driven by pilot. Everything is driven by this control system. So it has to be autonomous and highly efficient. So this area can be powered by machine learning. How? Okay. So first of all, let's start with some basics. Okay. So let's start with the quick basics. So rocket dynamics. So when it comes to rocket dynamics, what is this? This is nothing but degrees of freedom of rocket motion. So as soon as you launch a rocket, so these are all the different degrees of freedom your rocket can attain. What do you mean by degrees of freedom? Number of independent variables required to identify state of a moving body. Okay. When this rocket is moving, what are the different states you need to identify its dynamic behavior? That's the question. This is nothing but positive roll, negative roll, positive pitch, negative pitch, positive yaw, negative yaw, forward thrust, backward thrust, which is known as negative thrust. So this image will give everything about the roll. Where rocket can roll itself in positive clockwise direction and negative counterclockwise direction. Your rocket can able to yaw right and left, okay, in positive and positive clockwise and negative counterclockwise. Your rocket can do the pitch up and pitch down. Rocket can move forward. When it is moving forward, the forces opposing its forward motion fall into the category. It is nothing but a negative thrust. Okay, so we may need these 8 readings to define the state of a rocket. Okay, based on these 8 readings, we will finalize the dynamic behavior of the rocket when it is moving, when it's flying in the atmosphere. Okay, now how exactly we can control the rocket after we got the flight code, the flight command from the control system? How exactly we are controlling the rocket? We are controlling the rocket through 2 techniques. One is a thrust vector control. Another one is attitude control system. Okay, thrust vector control and attitude control system. So thrust vector control is powered by gimbal nozzle. Okay, if you take out a nozzle, which is where fire exhaust comes out, you can orient. Okay, you can the disposition. Okay, you can alter the position of the rocket. Okay, that is known as gimbal nozzle. So by doing those minor corrections willfully, you can alter the flight path of the rocket. This is known as thrust vector control. Then what do you mean by attitude control systems? Okay, so when rocket is in motion, there will be perturbation. Perturbation caused due to so many reasons. Due to these perturbations, your rocket will try to deviate from the pre-programmed trajectory. Okay, from the pre-programmed trajectory. So when it is deviating, okay, when it is deviating, all these 8 degrees of freedom will be measured, and that readings will be compared with pre-programmed trajectory, and the corrections would be made by a control system controller. Thereby, this attitude control system will do the essential through the vernier thrust, extra boosters, or cold jet exhaust. There are so many ways, okay, we can make the rocket stable. Okay, it's not only possible from the main rocket engine. There are other so many ways, so many extra structural arrangements we can able to control the rocket. So how exactly we release the controllability, that instruction, that accurate decisions comes from the control system. So attitude control system is what controlling the rocket to maintain its original flight trajectory when it is disturbed. Okay, when it is deviating from its trajectory. Okay, so now what is this attitude control system? So this attitude control system having a subsystem known as a reaction control system. Okay, reaction control system. So this reaction control system is nothing but a digital unit. This digital unit having a component, inertial measurement unit, which is known as IMU, and controller, primary controller, and devices for changing the angular position. Okay. So initial measurement is where we are taking the readings about 8 degrees of freedom, and we are sending those data to the controller. Controller is taking decisions. Based on that decision, devices will be operated and changing the position of the rocket. Okay. So this image is talking about cold jet exhaust. Okay, there will be exhaust spike out. Okay, and this is nothing but a full gimbal nozzle reaction control system. These reaction control systems we can usually find in satellites. Okay, So this reaction control system is the key element to control the to make sure the autonomous behavior as well as autonomous stability and control corrections of a rocket. Okay, and what is this? So when it comes to classical controllers, okay, maybe somebody of you already familiar with these words, classical controllers. There are so many control theories are available right now. Okay, in the next slide we will see those. Okay, the different control theories. So this is one category, classical controller. In the classical controller, we have a very important algorithm or a strategy known as PID controller. PID controller. So this is falling to the category RCS. Okay, this is falling to the category RCS. So we are now checking the block diagram of PID controller. PID controller. So you can see here the command inputs are the pre-programmed trajectory informations. Okay, coming here as a feed, coming here as a feed, and in the another end we are sending informations from the initial measurement unit. So this initial measurement unit taking the feedback from the rocket's 8 degrees of freedom. Rocket's 8 degrees of freedom. Okay. So what would happen? So these two readings are getting accumulated here, and these two readings are given to the PID controller. So this controller is doing the optimization by solving and taking the right decisions what to do. Those decisions will be passed to the device. That device will do the corrections. Thereby, your rocket will obtain new degrees of freedom. That new degrees of freedom is again taken into initial measurement unit, and those readings will be again provided here, and that will be checked again with the pre-programmed trajectory. And finally, once again, PID controller will take decision. This is something like happening throughout the journey of the rocket. Okay, so this is how controller controlling the rocket, maintaining autonomous stability, maintaining autonomous control. But this is quite old. This approach is quite old. This is known as classical control. What about latest approaches? Okay, so latest approaches are known as modern control and intelligent control. Latest approaches are known as modern control and intelligent control. Okay, so in the modern control, we have, we are sometimes calling this modern control as optimal control. So in the modern control, the key player is model predictive control. Okay, this is one of the strategy. This model predictive control could also be powered by or tuned by machine learning. Okay, and if you leave model control behind, come to intelligent control. This intelligent control is the leading hot research area. People are doing numerous research. Okay, so here their main aim to adapt, to blend machine learning to a control theory, thereby replacing, okay, or partially replacing existing control techniques. Okay, so there are certain aspects which is control system tuning using neural network. Do you know about neural network? Deep neural network. So deep neural network is part of machine learning. So we are going to use the machine learning in the control system to tune the control system. Something like tuning the PID controller using neural network, tuning the model predictive controller using neural network. Okay, so AI got here. Okay, and again there are some limitations because uh, reinforcement learning is the reason and is the feature of machine learning. Okay, but as of now, this reinforcement learning is not something which replace every control theory. Okay, this is actually now getting blended with existing control theories and producing their own version. Okay, it's still under hard research. So we can conclude here Even though industry is nowadays doing the classical control and modern control, maybe some low depth level of model control tuning with the neural network. Okay, but definitely in future, in the near future, due to the active research going on under the category of intelligent control using AI and machine learning, there will be so many techniques will be evolved. Those techniques will be replacing the existing control systems completely, and these rockets autonomous stability and control will be powered by sooner the complete intelligent control systems. Okay, so this is how we can use the research. Like we can do the research, we can apply the machine learning on rocket stability and control. Okay, so who is this guy? Lars Brockmore. Lars Brackmore. Okay, so this guy is the reason behind the development of SpaceX Falcon 9 autonomous landing behavior. Okay, this guy developed the algorithm. This guy and the team developed entire algorithm. Okay, about the SpaceX Falcon 9 autonomous landing. As soon as it discharges the payload to the orbit, it comes back and landing on the surface. Okay, so how exactly he achieved it? His objective, his control theory objective is nothing but when the rocket touching the ground, it has to go zero velocity. Okay, it has to go zero velocity. At the same time, it has to keep minimum fuel at least. Okay, without completely depleting the fuel, the rocket has to land. But at the time it land the rocket, the velocity should be zero. So with these two equations, with these two considerations, he developed the algorithm, and this algorithm is known as GVX Gen, CVX Gen actually, CVX Gen. The term CVX stands for convex optimization. Convex optimization. Okay, so what is this convex optimization? How it related with the machine learning? How it related with control theory? Okay, we really need to understand that because this guy made a revolution. Okay, this guy made a revolution. Because of him only, SpaceX now able to land its rockets safely, and because of him only, the SpaceX sooner going to land a rocket on a Mars surface. Okay. So what is this convex optimization? So convex optimization problem is something known as optimization. Okay. Optimizing, solution optimization. So here the key inputs are convex constraints or non-convex constraints. What is these constraints? These constraints are nothing but inputs, challenges. Okay, while the rocket attaining perturbation got disturbed its flight path, or while the rocket coming back to land, okay, it will suffocate. It will suffer with the perturbation. Those are known as constraints or challenges. Those challenges, constraints, those feedbacks will be passed to the controller, right? So these are known as convex constraints. These constraints will be taken in inside the solution. There will be optimization. This optimization is powered by convex optimization. Okay, convex optimization. So convex optimization is pretty much similar to gradient descent, pretty much similar to Adam optimization, pretty much similar to the various optimization techniques we can see in machine learning. But this convex optimization is supporting to the both area, supporting the control systems, supporting the machine learning. Okay, because it could be blended with control systems and also it could be blended with machine learning, especially reinforcement learning. Okay, so this convex optimization, exactly the strategy technique Lars Brockmore used in his onboard flight control softwares. Okay, so how we can understand these optimization in the simple norms. So if you check out these two plottings, the very first plotting is actually an optimized uh, convex. Second one is non-convex. Okay, so here you can find local minima, so many local minimas, but in the very first image, you find only the global minima. So the optimization is at their convergence. Here, the optimization is not converging properly. Okay, so when the data given to the control system, your system having so many constraints, and the environment is just looking like this, confusing, problematic, that will be converted to this state. This is a converged state. Thereby, the decisions would be taken could be accurate. Okay, this is the theoretical idea of convex optimization. So SpaceX Falcon 9 used this algorithm, okay, in their onboarding flight computers. Now, this paper, okay, released by Lars Brackmore on August 2010. Okay, in this paper, he mentioned everything about his idea of landing the rocket or spacecraft on a Mars using convex optimization. Okay, and this paper is talking about how we can apply reinforcement learning, which is machine learning, to deal with convex constraints. Okay, and yeah, to deal with convex constraint. So we can assume here these control systems could be blended with the machine learning, and machine learning is optimized with a different optimizer, and one of the optimizer is convex optimization. So everything is interconnected, right? And active research work is also going on. This is the proof. Okay, great. Now, this is actually quite important. What is this? When it comes to tutorial point of view, okay, because whatever we have discussed, we really need to see it in a code form and simulation form, right? So this is known as Open AI Gym Environment. Open AI Gym Environment, okay. So when you navigate yourself through this web page, you can find so many existing environment. I mean, already built environment. This is one of the environment known as lunar lander. So this environment is giving you an access to draw a simulation. I mean, use the existing simulation. This is the existing simulation. On the lunar surface, this lunar lander is landing. Okay. So it is something like a resemblance of autonomous landing, right? So while it is landing, it has to land on the right way, on the right landing pad. It has to land. Okay, that's the objective. So what you will do, you will fetch this environment in your notebook, and you will induce the behavior of this lunar lander using different RL policy. What is RL? Reinforcement learning policy. So by inducing those policy, this machine learning agent, which is lunar lander, obtaining some dynamic behavior. With that dynamic behavior, it could easily able to explore the environment. Okay, with that skill, it can easily able to land on the right landing pad. So this is how I can give the short introduction about the oral environment. Okay, so how you can convert this into reality? In reality, instead of the simulation, here this is just a simple simulation. Instead of this simple simulation, you create the well robust simulation which covers everything about the atmosphere. Okay, the real time projection, everything you are covering in the simulation, and your agent is going to be the rocket. So you are doing simulations at first. When it comes to reality, you are just using edge computing, you are feeding everything in your system. So now your rocket, technically a robot, which is discussing with the actual environment with the simulation data. Okay, thereby we can make sure the pre-programmed trajectory, everything, and thereby we can make sure the controllability there. Okay, this is how we can implement whatever we could able to learn about the our environmental projects in future in real projects. Okay, and this is another one example. This environment is also available in OpenAI Gym. Okay, OpenAI Gym. You can see rocket is just descending. Okay, descending, and now it is landing exactly on the landing pad. Okay, This is a resemblance of Falcon 9 landing behavior. Okay, so this environment is available. We can easily fetch this environment, but we really don't know how to induce the learning behavior of the agent. How the agent would able to learn the environment and map that learning with the pre-programmed trajectory and obtain the right landing. Okay, that part requires support from different RL algorithms. So we need to learn RL very well, reinforcement learning very well. Okay, at one stage we will apply those learnings as a policy, as a behavior here through the code. Okay, thereby you can easily make your rocket to land successfully on a simulation. Later, when you will be getting into real environment, you can extend this project into versatile levels. Okay, you can consider real environment simulation there. Okay, similar to this, and you can build everything there. Okay, just like this, we have to improve our quality of learning. Now, just like we talked about pre-built environment, we can also able to build our own environment. Okay, in a tutorial point of view, we can also able to build our own environment. So it's maybe the code length would be a little bit more, but again, it can be achievable. It's not a tough, it can be achievable. Okay, we can easily learn it. We can build our own custom environment with the color we want, with the agent's shape we want, we can easily make. So what I want to tell you is the taxonomy of other algorithms. If you take out other algorithms, it can be divided into two: model-free RL, model-based RL, and there are so many algorithms are listed here. So if we could able to learn these algorithms very well, you can directly implement these algorithms on any environment, existing environment or your own environment. You can boost up your skills. Okay. And great, this is the paper. These are the papers. Example, okay, current research, how learning, how reinforcement learning is utilized for rocket-powered landing guidance and control. Okay, people are doing the research, latest research, 2021. You see, okay, and this is another one paper talking about how effectively reinforcement learning could be used in spacecraft control applications. Okay, so this paper is also there in the website. It's a very recent one, 2022. So it's an active research. People are doing the research. Okay, using reinforcement learning over the rockets, over the spacecraft. Okay. Now this is another distinct domain which is known as terrain relative navigation. Terrain relative navigation for autonomous planetary landing powered by computer vision. So what you see here, you are just seeing the spacecraft which is carrying the rover, that rover to be posted on the Mars surface. Okay, so this is the flight profile. This is the flight profile. This flight profile is not a pre-programmed one because maybe because this camera systems. Okay, the camera systems which is placed under the rover is nothing but camera based mission vision, which is actually capturing everything and identifying the patterns. Thereby it identifies the right spot to land. Okay, so as soon as it takes the readings about the Mars surface, those data is just given there, and intelligence system taking decisions to land or not, and according to that decision, according to those readings, it just extend its profile. Okay, and landing on the right spot, getting landed on the right spot. Okay, so this is known as terrain relative navigation powered by computer vision. Computer vision is powered by machine learning. Okay, and this is how things would done normally. So this is the surface. So camera-based machine vision is taking readings on the surface, where the crutches, where the potholes, where ups and downs or not. I mean, where it can able to see the smooth surface at that based on that place, it will land the rover. Okay, this is known as terrain relative navigation. Without AI, without image processing powered by AI and computer vision, this is not possible. This is not possible. Okay. And another important thing, our autonomous rocket landing, SpaceX Falcon 9 and Starship. Sooner these rockets will be landed. I mean, the Starship will be landed on a Mars. Okay. And definitely, while it is landing there, it has to do the survey about the landing area, landing pad. And this image is all about landing Falcon 9 on the landing pad. Okay. So when it is coming down, it has to make sure it is in the right path to land. How it is making sure? By using computer vision. By using computer vision, you keep on taking the reading about the landing pad and it would land. Okay. So computer vision playing a crucial role there, and computer vision is powered by machine learning. Okay, please. Now, see, these are the papers doing research over this particular objective. Here you can see the recurrent imitation learning. So here they are doing so many blending of the existing deep neural networks. Okay. And this is again talking about safe lunar landing. Safe lunar landing, how we can do the safe lunar landing. So again, these are all hard research topics. People are doing research. If we come to know about AI, if we come to know about camera-based machine vision and how to apply those on these kind of projects, definitely we can build up our skills and we can be fit for these kind of profiles in your future. Okay. And this is our final chapter. So digital twins. Okay, what is this? Digital twins. Personalized feature for computing for complex systems. Digital twins. Okay, what is this? So check out this slide. So we have a real space. We have a virtual space. Okay, we have a real space and we have a virtual space. So real space is nothing but your physical rocket. Physical rocket. Virtual space is nothing but digital version of the physical rocket. Digital version of the physical rocket. A to Z about the physical rocket you can find in the digital version. Okay, in the digital version. It's something like a Xerox. So not a duplicate, complete Xerox, okay, of a real rocket you can have in a digital form that is known as digital space rocket, a digital space or virtual space, okay. So digital twin is nothing but if you take out any device, anything, if you take out anything, your moving car, computer, if you take out anything, if you could able to create its digital form with all the functionalities within it, okay, and if you could able to make a connection, data transfer connection between your physical device to the digital device, okay. So what about happening in a real time in the real rocket could be, I mean, real device is measured and validated and troubleshooted in the digital domain, I mean, digital device. Okay. Thereby, necessary decisions has been made, rectification decisions has been made if there is an issue during the motion, during its functionality. Okay. So this is how things work out. So a digital twin is nothing but simply, for example, rocket. We are designing, building, fabricating, assembling, and we are completely making a rocket. And we are sending the rocket. And it is just discharging everything and coming back to land. This whole thing is framed. Okay, this whole thing is just converted into digital form. Okay, the whole thing, starting from the designer till the land, can be converted, can be made into digital form. Okay, so during the real-time initialization, during the manufacturing, if there is any issues in the manufacturing, okay, and the data that is taken during the manufacturing fed into the digital domain, and the simulation is working on there, will give the result. No, this manufacturing is wrong. There's a fault. There's a structural damage. Definitely there will be a damage. Okay, at that moment during the manufacturing, it will tell the story. So when exactly NASA used digital twin in 1970? When United States Apollo 13 failed, was about to fail. There was an oxygen tank explosion. So Apollo 13 was about to fail. So at that time, the people who were sitting in NASA, okay, NASA already they developed a digital twin. Okay, they run simulations because the real-time data transfer is happening there. Okay, whatever happening in your real rocket, just happening in your digital rocket. Okay, so real-time transfer happening there. So the digital rocket keep on running the simulation and give the solution what to do. Based on that, they have done it and they just solved everything. They rescued the crew successfully. So this is where they have used the digital twin for the first time. Okay. So for the more details about digital twin, this is it. So we have a real space. Okay. This real space is nothing but a complete rocket, and we have a digital rocket. This digital rocket is nothing but rocket model actually. This model having everything about the rocket, the design considerations and performance considerations, real-time dynamic behavior alterations, everything. Because here in the real rocket, we are placing so many sensors in our unit, right? So those sensors taking readings and keep on sending those readings to this digital model. So based on those readings, this digital model will perform the simulation, will monitor the result, will do the diagnosis, will take the predictions, and if there is any wrong with the prediction, it will do the optimization. So we can apply the machine learning in this area, okay, after the monitor, while doing the diagnosis, while doing the prediction, if there is any issues to optimize it, we can use the machine learning, okay. So people are trying to find out and doing greater research here to replace this digital doing digital form, this optimization, troubleshooting, everything could be done. They think could be done with machine learning, and they are doing it. Okay, so after the optimization is done, the corrections coming from these predictions, that would become information, and that information coming to a real space, okay, and based on that there will be rectification happening here, and finally it will do a safe flight, okay. So and we can use this digital twin even when we start to design, even when we start to manufacture, even when we start to do some servicing, everywhere we can use the complete rocket could be troubleshooted using digital twin, could be designed using digital twin, could be manufactured using digital twin, could be tested using digital twin. And digital twin is powered by artificial intelligence, which is machine learning, okay? Because people are doing the research. These are all the famous digital twin solution providers: Azure, Siemens, IBM, Cisco, Oracle. Okay, if you do the browsing, you will definitely find more organizations building digital twin services. But coming to active research, this is the paper, Rocket Engine Digital Twin, Modeling and Simulation Benefits. Okay, you can find the paper because this is a very recent paper and people are doing research. Okay, digital twin, modeling and simulation benefits, and how exactly we can enhance the digital twin using reinforcement learning. Okay, so machine learning came here. Reinforcement learning is part of the machine learning. So using the reinforcement learning, we can enhance the digital twin. People are doing research. Okay, and this is the very recent paper, 2019. Okay. Yes, any doubts? I think someone raised a doubt. Can be done. Yes, of course, obviously. Any device, if you take out any device, any physical device, people are trying to frame digital twin for a human body, because diagnosing, medical diagnosing would be quickly done. Okay, so they are making human model, digital model, and connecting it with actual human. Okay, if when we are going for a treatment, if maybe the readings coming from our body could be sent there, and they're taking decisions, giving it back. Okay, they're doing the research. We can do we can do this digital twin on any devices, anything. And this is another one leading research paper, digital twin reality for control system. Like I told already, control system is where also we can use the digital twin. And this is another paper, digital twin for intelligence sensing. As wherever you find the word intelligence, please aware it is talking about artificial intelligence. Okay. So these are the hard research topics. So far, we have covered 3 chapters. First of all, we checked about how we can design a rocket using scientific machine learning. Then we discussed about how we can power up autonomous behavior of spacecraft, autonomous behavior of rocket, autonomous stability and control, particularly with the help of machine learning. Then we talked about terrain relative navigation, how it could be powered by machine learning. Okay. Then finally, we talked about digital twin. A2Z survey about the rocket in reality could be, if there is a malfunction, could be that particular malfunction identified, and necessary corrections to be made through the digital form of the particular rocket. Okay. So in order to make the corrections, we can introduce some artificial intelligence there. Okay, we can build everything. We can create a digital twin. Okay, just like this. So this is the active research area. So in your academic program, if you, I mean, if you are doing academic courses, second year, third year, if you please build up some goals, something like learning artificial intelligence, learning reinforcement learning, and applying it over any technology. Okay, and trying to predict and trying to make a dynamic model of a system, and putting those there and predicting everything, maintaining the controllability. Definitely, these areas are hard areas, leading research areas. It will definitely give you job, okay, in space tech, not only in space tech, in technology. Wherever people are crazy about technology, definitely you will get the job, okay. So let's get into the career opportunities in space domain with AI and ML. So I just give 2 links, okay, just 2 links. So many links are there, okay. If you check out these 2 links, you will find so many jobs. So spacecraft subsystem developer, geoinformation data engineer, data engineering dealing with machine learning, GNC, control navigation guidance, AI engineer, image processing, AI engineer, machine learning for robotics, software development engineer. So these titles recovers the foundation AI. And in order to fetch this job, we should be doing, I mean, we should be aware of AI, and with the help of AI, we should be knowing how to do some projects, at least a tutorial level projects, some internships, some program, training program, skill enhancement program, definitely would be helping. So with that basic stuff, we can definitely approach these industries. Okay, definitely we will get an opportunity. We can compete, right? We can get the empowerment. We can compete. So please consider. And finally, in space tech, I mean space tech in India, not only ISRO is doing now space acceleration, okay, because ISRO is tied up with the InSpace NSIL. They are, so lot of private bodies are also doing space exploration. So many opportunities out there. Okay, they need a person who is having some talent with the technology. Okay, the technology improvisation they will do, they will train you, but they need some calibration in the students. And finally, if we take out the globe, more than 130 space government organizations, more than 150 R&D, more than 10,000 companies you can find regarding space exploration, more than 5,000 investors. Okay, this is going to be a nice career, right? Yes. And yeah, so regarding ourselves, because I discussed about how ML applicable in rocket science and how rocket science is particularly helping space exploration, thereby how we can connect the learning to the global space industry. So how exactly we Spartificial helping this? Okay, that is what I'm talking about here. So we are offering programs. If you permit yourself to these programs, there will be a learning from the scratch. If you take out Python, I mean, in order to learn AI, Python is required. So we start with Python, we learn AI, we do some mini projects, then we get into our code project. So based on the code project, we define our curriculum and we split our program. Okay, so this is our program. This is one of the program currently active. Autonomous rocket landing with AI. And this is another program, Mars exploration with machine learning. And this is another program, astronomical data science with Python. Okay, so more details about these programs you can find in Instagram page, in LinkedIn page, in website. Okay, or you can contact this number, you can get more details. Okay, or you can use this QR code to know more about that. And obviously, yeah, so this is all about us. After the, I mean, at the end of the course, there will be internship opening. So at that time, you will choose your own area of interest of project. Okay, we will assist, we will give the mentorship, we will monitor everything, and you will accomplish everything, and you will get your internship. So this is something like end-to-end learning from scratch, then implementing with your own interest at the end. Okay. So the journey, if you are choosing hours to do, the journey completely going to be helping, and it will definitely give you good knowledge. And at the end, you can use these fundamental knowledge to get yourself in good industries. Okay. Yes. 1 second. Someone ring the bell. The course by Spartificial. Autonomous landing is taken by you. Yes. How many classes are done? It, as you said, it is active. No, no, no. One course is active. Okay. Another course is about to begin. Another batch is about to begin. That is what I mentioned about active. Okay. One batch is on active. Another batch is about to begin. Okay. In recently in 5 to 6 days, I think. Okay. Yeah. That is taken by me. I'll be teaching RL from scratch there. I'll be teaching AI from scratch there. I'll be teaching Python also from scratch there. And we will apply RL on control issues. Okay, we will develop our own custom environment, and we will induce dynamic behavior of these RL policies to an agent, and we will check how rocket is learning effectively on a landing pad. Okay, everything will be done in the course. Okay, guys. So this is it. Yes, 1 second, 1 second. This is it. So yeah, you can find me in the LinkedIn. Okay, and or you can write me about any queries. And this is what we are offering. And yeah, now it's time for your queries. Okay, please carry on. Again, Jatin. So yeah, Arjit Saxena. I am from triple background. I don't know much about coding. Only I have good knowledge about C. That is good enough. If you know C++, you can easily learn Python. Once you easily learn Python, once you become competent enough there, you can easily gain skills in data science. With that, yeah, we can achieve anything. It's all matter of sitting and working. That's it. Okay. So you can do, right? And Jatin Minocha. During this course session, what we talk how to prepare your own research paper and guidance regarding the same. Obviously, when I mean, you know what, when you are committing into something, okay, when you are committing yourself to your learning, to your technology, you automatically develop interest about that. We can do browsing, Browsing is the art, right? So we can find so many journals pages where they are listing out the current work. We need to read that work, we need to read the abstract, we need to read the conclusion. That way we can able to understand more about what you are learning if you are getting into the course. Okay, thereby at the end of the course, you will be mastering your foundation. With that foundation, you can choose your own problem domain in the internship, and or even after the internship, if you are interested, you can you can again work there, get your new problem, because you will learn the foundation, right? Anyhow, with that foundation, you can do a lot of exploration. So it's all about collecting the information regarding the problem statement. That's it. Okay. Yeah. Any other doubts, people? Now it's you can ask. Any doubts you can ask. Okay, I'm here to answer.
Hello, sir.
Yeah, please.
Sir, I have a
Priyansu.
doubt. Yes, sir.
Okay. Yes.
I have a question, sir.
Hmm.
Sir, I mean, what kind of technology was used during the Apollo missions, and how it is different from this convex optimization problem or the
Yeah.
current landing
So
programs?
yes, yes. Current landing program was in there in 1970s. Okay, they have used classical controllers. So I discussed about classical controllers, right? One coming with the PID controller. So they have used PID controller at that time, the classical controller at that time, to maintain, I mean, to monitor the autonomous stability and control when there's a perturbation happening around the rocket. I mean, when rocket deflected from its pre-programmed trajectory, it has to compare to the programmed trajectory, right? So in order to work out there, they have used classical controllers. Nowadays, what they are using intelligent controllers. I mean, they are slowly, pushing themselves to intelligent controller adaptation. So autonomous landing is power in SpaceX Falcon 9 powered by classical controller, not classical controller, modern controller, convex optimization, and machine learning. Okay. Yeah.
Okay, sir. Thank you.
Yeah. So this is how technology got developed nowadays. It's comparatively better. Okay. So sooner in decades, all those control systems will be replaced by intelligent control systems. Yes. So there are two questions. Kavana D. Rajan. Is there any specific cloud computing platform used for all the activities mentioned in the session? Yes, of course, digital twin service provider. People are using Azure for that. Okay. And Google service provider also providing service for digital twin. Okay. And when it comes to machine learning, people are using cloud computing there. Okay, because Azure and GCP and Amazon Web Service, everything is cloud based. People are building their machine learning in cloud and deploying it in cloud, saving the model in cloud, continuous monitoring, continuous development, everything they are doing with respect to cloud. Okay, the standard industries definitely would go for that only. So obviously, cloud computing is there. And Mandan Rathod. Hello, sir. I am from CSC background. I am interested in missiles guidance system. I want to learn in deep. Can you please guide me? How should I start? So you should start from control, guidance, and navigation. Okay, you are from CSC background. So you need to fetch a book, control, navigation, guidance. So we need to cover some theory at first. Those are nothing but control systems, complete control systems. Okay, the complete control system oriented towards GNC. Okay, so you need to learn that at first. Along with that, you have to achieve. I mean, you have to commit yourself for the programmatic learning skills, Python and machine learning. Okay, or MATLAB. Okay, just something like that you need to learn. So after you learned these foundations, you need to do some projects, real projects, designing the complete missile, okay, and in a simulation and applying some machine learning there, to induce the autonomous behavior. So those kind of checking you can do. Okay, after you design, after you developed, first starts with some book reading. Along with that, starts with some program learning. Then combine it, develop your own project. Definitely, you can achieve it. Okay, and yeah, and again, Jatin Minocha. As we know that building rocket required good knowledge of physics, do we still require the same in this area? Physics. Building rockets. Okay, you know what? If you want to do everything, you can do it quickly. I mean, if you want to build a rocket and if you want to know about the operating conditions of the rocket, if you want to know about the stability control of the rocket, if you want to know about autonomous landing of the rocket, definitely it would take some more time. Okay, more time. So you need to divide your area of interest. If you only want to build a rocket, I mean, to design and development of a rocket, okay, you can commit yourself in that direction. If you want to work towards the autonomous stability and control of a rocket, you can commit yourself on that region. If you want to know more about propulsion unit and the structural unit of the rocket, you can commit yourself there. Okay, when it comes to design and development, you don't need physics, but you need some philosophy, some structural philosophy, structural dynamics, and yeah, fluid dynamics. You may need those foundations, okay, and those foundations related to physics, obviously, but we don't need to learn the entire physics, okay. The physics, whatever we have known so far, is good enough. We just need to get into state of the art of how physics getting applied there. Based on that, we can start our journey. Okay, Jatin. And Khaniga Mageshwari. Khaniga Mageshwari. Hello, sir. I am from physics background. I have a good knowledge of ML2. How to start doing project, platforms or resources. So you have a good knowledge on machine learning, great. You are from a physics background. How to start doing project. So being a physics background, I guess you know more about current ongoing physics research. Okay, current ongoing physics research, something like God's particle prediction. Okay, something like weather prediction, something like structure, complete surface anomaly detections. Okay, these are related to physics. This physics is moreover related not only to geography, it is related to dynamics also, right? Physics dynamics. So physics dynamics is related to controllability, control of any dynamic system. So that control of dynamic system is powered by machine learning. Okay, could be powered by machine learning. So you don't need to start from platforms or sources. You just need to find yourself the right problem statement. Okay, then you can find some sample projects on the internet, on the website, on the YouTube. Okay, or you can commit yourself internship here in Spartificial after the training program. So it's something like that. Okay, mentor support will be there, and you can define your own problem statement. Just because you know about machine learning, you can directly submit that there in your problem statement. Okay, that way you can complete it. Again, yeah, Jatin Vinochu. Yes, thank you, Jatin. So Kanika, is that clear? Whatever I just told about your last question, physics background question.
Yes, sir.
Okay, okay, great. Okay, guys, any other queries? Yes, as I belong to Triple E, so taking autonomous landing course will help me. Okay, so as you belong to Triple E, okay, what do you mean by inertial measurement unit? So inertial measurement unit is like an electrical electronic system, right? And rocket's internal system is all about, I mean, to be precise, if you want to apply machine learning in rocket, that machine learning exactly where we are, sorry, 1 second. If we want to apply machine learning to the rocket in control area, we will learn more about control systems. Those control systems related to inertial measurement unit. Inertial measurement unit will talk more about electronic systems. Okay. So obviously, you can able to divert. I mean, you can able to commit yourself. Okay. We are not actually learning about power systems. We're not learning about electricity, electromagnetic theory. We will learn about how we can obtain informations from electronic systems. Based on that information, how we can obtain the autonomous stability and control using machine learning. Okay, okay. So that's where you can apply everything, I guess. As MU skills are going to be used, or not like avionics section. MU skills. Is that MU skills or ML skills? I guess it's ML skills, right? Uh, uh, yeah, my skills. Okay. As my skills are going to be used or not like avionics section. Okay, it is not going to be avionics. Okay, like I told already, avionics is completely different. Okay, but avionics include the part flight computer. Am I right? Avionics include the part flight computer. Flight computer includes control theory. Control theory need machine learning. Okay. And to pre again part of the avionics, all wiring systems, all those internal circuits, everything coming from triple. So it's a core, okay, it's a core domain. So you don't need to worry about that. So learning machine learning and applying the machine learning on autonomous behavior of rocket, not going to, uh, I mean, push you out of the core, out of your own core. Definitely, it will lay down there somewhere. Okay, you got it, Aljit Saxena. Yeah, great. Okay, guys, any other doubts, queries?
Hello, sir.
Yeah, please.
Yes, sir. My name is Jasmine Fernandez.
Mm.
Yes, sir. So I have done graduation in IT engineering and post graduation in AI ML. So I wanted to ask, like, is it required to have a master's degree in astrophysics and astronomy to get a job in like some space agency?
Okay, so you are already done IT, right?
Yes, sir.
And masters in astro.
No, so master's, like postgraduate diploma in AI and ML.
Okay, again, it's not about the certificates and degrees, and it's all about our exposure, the explorations we have made on this domain, and how much knowledge we have gained. Okay, and if you really want to get into space agencies, that's what you said, right?
Yes,
You
sir.
want, yeah, if you want to really get into space agencies, what I suggest, do more projects, whatever you have learned so far. Do a lot of space related projects. Choose your domain. You said you have done postgraduate in astrophotography, right?
Oh, no, no, sir. Post graduation diploma in artificial intelligence and machine learning.
Okay, okay. So you have a good background in AI. Okay. So you know about AI, you know about data science, you know about Python definitely. So you must have done so many projects. So with these skills, what you can do, you can commit yourself into space exploration domain and do more projects. You can choose your own domain in space exploration also because there are so many domains. Something like application of machine learning in spacecraft dynamics, application of machine learning in rover dynamics, application of machine learning in this environmental detailing. Okay,
Okay, sir.
astronomical data science. Like that, you can divide your domain. You just develop your own interest and divide the domain. Choose a very particular domain. In that domain, do numerous projects, number of projects. Okay, and those projects shouldn't be talking about tutorial point of view. Okay, it should talk about more intensive. Okay, more intensive projects, long time projects. Okay, it's not about certification. It's all about how you can put yourself there and achieve the skill. And based on that skill, you have to keep on trying. Okay, once your skills are good enough, definitely they will consider.
Okay, sir.
Yeah,
Thank you so much, sir.
yeah. Okay, guys, any other queries? I would request you to share the recorded link of the session. I can go through with all the content. Okay, I think the admin of our meeting will do that, right? Yeah,
Yeah, we'll share the recording on our YouTube channel and everyone will be able to access.
yeah, great. Yeah, thank you, Governor D. Rajan. Thank you, Jatin. Thank you, Arjit. Yeah, thank you, Jesslyn. Yeah, great. Thank you, Advait. Okay, guys. Yeah, thank you. Thank you. Any other queries? Any other questions?